got main energy levels. We say electrons can't exist between them. It explains the hydrogen emission line spectra of hydrogen perfectly. Yay! It just doesn't work for any other elements. Oh. Well, this is kind of like why do electrons get sucked into the nucleus? We're not really sure why it doesn't work for anything but hydrogen, but we're going to keep it for now. Because it's the best we've got right now, and science is tentative. Science is changing. So this is just a modification to Rutherford's planetary model. Very often this is just taught, and this is the simplified version you learn in junior high and in physical science. It's just taught as the planetary model with Bohr's additions to it. We don't even recognize that there was one before Bohr came along with it. Okay, so now we're going to sidetrack again. So we've got this nice planetary model with the addition of energy levels. Good, we got this thing. Okay. So, remember that Einstein said, it's a wave, it's a particle, it's a wave, it's a particle, it's both! So Louis de Broglie comes along, French physicist, and he says, you know what? I think it's more than light that's up to this sort of trickiness. I think electrons do the same thing. And actually, I had not encountered this story. A student found this, that de Broglie writes his PhD thesis, writes his doctoral thesis, and his advisor basically looks at him and says, I'm not qualified to grade this. I don't know what you're talking about. Go ahead and send a copy to Einstein, see what he has to say. And he does. He sends his doctoral thesis to Einstein. He says, brilliant, perfect, this changes everything. Needless to say, he passed his doctoral thesis. When your advisor tells you to send a copy to Einstein, yeah, you get your doctorate. So, de Broglie says electrons act like waves as well. So we knew that they were particles, because who said they were particles? Thomson. Way back in 1897. Thomson said electrons are particles. They move my paddle wheel, they're particles. De Broglie comes along and says, dual nature. They behave as waves also. So, if they behave as waves, remember we can have a wave equation, right? You're all in a high enough math that you've seen things like sine curves. You can take a graphing calculator and you plug in a sine function, you get this pretty little wave that goes like this. Woo! Okay. So, if electrons are behaving as waves, guess what? There are equations that describe their motion. Woo-hoo-hoo-hoo-hoo! This is exciting. It is. So, I want you to take a moment and do a little thought experiment. Now, first of all, so the way he plugs this into Bohr and Rutherford's model. This is okay. We've got these electrons at these particular energy levels. Those energy levels, if we solve the wave, if we write an equation for that wave, there's a frequency associated with it, Planck connected frequency to energy, and it's all going to work. Those frequencies will equal the energies that were predicted, and it does, as it turns out, which is pretty cool. So take a look at your hand. Get our hands out again. There are a bunch of atoms in there. Each of those atoms has electrons orbiting around a nucleus, right? Or outside a nucleus someplace, right? Good, yeah. They're particles. They have a physical presence. That's why you can smack something and it moves. Good. Okay. Now, they're also waves. So each one of those atoms in your hand, with all those little electrons outside the nucleus, is behaving as a wave, and each little tiny discrete point on your hand has some equation to describe the motion of that wave. And so when you move your hand, all these little particles are moving, except they're all little waves. They were already moving before you moved your hand, and now you're moving your hand. So it's wave equations, and wave equations, and wave equations. You're welcome. Enjoy 3 a.m. Okay, so de Broglie says electrons are particles and waves. You're welcome. Okay. Now we get to two of my favorite particle physicists. Oh my God, I love Werner Heisenberg. There, I've said it out loud. He's wonderful. He is. Werner's awesome. So, Werner Heisenberg. Werner comes along and says, okay, fine. These electrons are, we're going to talk about that in a second. These electrons are particles and their waves. And there is an equation that describes their motion and their position and location, right? Well, Einstein said that light is a what? Particle. Einstein's wave-particle duality. So Einstein calls it a photon. We have little photons. Now, what did we say about particles when they strike something? They move it. Okay? So what Heisenberg says is that when we're attempting to observe an electron's position, because the electron is both a particle and a wave. Now, you all know that if you're observing something, so observe your pencil, your paper, whatever. You observing that thing means that a wave / photon of light is striking that object and bouncing back and entering your eye, correct? You all know that. Good. So what Werner Heisenberg says is that when you observe an electron, remember electrons are really tiny little things. When you observe it, the act of you observing it means a photon has to strike it, and the act of you observing its position changes its position. The act of observing it changes it. Now, as a sidebar, I will say that I think this is a metaphor for everything else that follows in your life. Heisenberg's uncertainty principle is seriously a wonderful metaphor for everything in your life. The act of observing something changes it. You can never know what that thing would have been without your observation because the act of your observing it changes it and thinking about it changes blah, 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 blah. So again, add that to your 3 a.m. list. So that's Heisenberg, in the sense of being known as the Heisenberg uncertainty principle. It says we can observe the speed of an electron, or we can observe its location, but when we observe one, the other's going to change. This leads to the old joke about Dr. Werner von Heisenberg driving down the road, and the Polizei stop him. Nee, nor, nee, nor, nee, nor. And they pull him over. And the Polizei walks up to the car and says, "Sir, do you know how fast you were going?" And Heisenberg says, "No, but I know where I am." Because you can't. Do you know how fast you were going? No, but I know where I am. Okay, anyway, didn't get him out of the ticket. So, Schrödinger, another of the German particle physicists, comes along. Schrödinger looks at these electrons. You'll all start laughing sometime this afternoon or at 3 in the morning. Schrödinger comes along, looks at these electrons and says, okay, they're waves, right? Because who said they were waves? Who said electrons were waves? De Broglie. De Broglie, yeah, Louis de Broglie. When Schrödinger does a set of equations that treat them as waves, he finds that there are only certain frequencies that will make those equations work. Now, that ties back nicely to the stuff, to Bohr's stuff, where there are certain amounts of energy, certain frequencies, certain energies, it's all connected, great. Now, you know that an equation can describe a line. You know this. You know, I hope, that an equation can describe a three-dimensional space, yes? You can write, and trust me, we're not going to do it in here, and I'm never going to do it in my life, but you can write an equation which describes a three-dimensional space. When Schrödinger writes these equations, he finds only certain values work, and if he, in essence, draws the picture from those equations, he gets these regions of space, these physical shapes. So, Heisenberg says we can't know both where it is and how fast it's moving. Schrödinger says, yeah, but I've got this region of space where I think it is. From that, we end up with what's called the quantum model. This is the most modern way of thinking about the atom. So, it says it's got a dense central nucleus that's protons and neutrons. That comes straight from Rutherford. That hasn't changed since 1911. It says that electrons are in specific areas outside the nucleus and that they're always moving. That's pretty closely pulled from Bohr's. That's not all that different from what Niels said. And still also staying around from Niels Bohr's model is that we have main energy levels. We have different levels of energy that these electrons can live in. What Heisenberg adds to that is that we cannot know the position of an electron. But Schrodinger's wave equations, when we solve those, show us that even though we can't know exactly where the electrons are, we can pin down an area that they're probably going to be in. We can pin down a region where the probability of finding an electron is very, very high. That comes from Schrodinger. So these areas where we have a high probability of finding an electron are called orbitals. So if we go back to Rutherford's ideas, the planetary model, we had electrons in orbits. Now we've thrown out orbits, and what we have are these areas that are called orbitals. They're three-dimensional. They're no longer two-dimensional. If we stick all of these orbitals together, because there are a bunch of them, Schrodinger's wave equations give us, oh good heavens, hundreds of individual independent orbitals. We stick all of them together, what it ends up looking like is a wet gumball that got dropped in a bag of fur. Big. It's a big fuzzy cloud. It's this, you could think of a BB in the midst of a packet of cotton candy. It's a little tiny dense thing in the midst of this big fuzzy cloud. Are the electrons everywhere in that fuzzy cloud? No, they're someplace in that fuzzy cloud. Can we pin down exactly where they are? No, Heisenberg says we can't. That's what's sometimes referred to as the electron cloud. And so the quantum model is dense nucleus, electron cloud around it comprised of these orbitals, these high probability areas for finding an electron. Okay. We've now talked about multiple models of the atom. The two that are the most recent historically are the planetary and the quantum. So what everybody wants to know is, well, which one's the right one? You should be used to this by now. Both! It's planetary, it's quantum, it's planetary, it's quantum. It's both! Neither of them is a physical atom. Neither of them is the whole truth. They both give us tools to think about how atoms behave and how atoms function. So neither of them is wrong. Neither of them is right. They coexist, and we need them both to think and talk about atoms and their behavior. Clear? Good? We're going to